Hello and welcome once again. In the previous lecture, we saw some simple examples of linear equations with in a form where we could infer the row, the range dimension, the null dimension, and all that very easily. So it maybe gave us some nice ways to infer how the solution will look like. Now there was that one issue that how do we get all those zeros in the matrix, right? So why is it okay to have all those zeros? If you don't have zeros, what do you do? How do you get it to that form? And that's what you do with what are called elementary row operations or Gaussian elimination, the way we describe these things. Okay. So let's do a quick recap. We've looked at vector spaces, linear maps. We know matrices represent linear maps and all that. In particular, in the last lecture, we saw how linear equation solutions to a linear equation depend very critically on the nature of the linear map represented by the matrix A, whether it's injective or surjective and all that. And in this particular case, we will now look at elementary row operations to get the matrix to a nice form and still not affect the solution. Okay, so that's the idea, and that's where operators will play a very important role, and we'll start using operators in a very direct way. Okay, so here's once again a reminder. If you have a general 3 by 3 equation, it will look like that. It would have a non-zero, possibly non-zero entries everywhere. You can do Gaussian elimination through elementary row operation. And what is that? Basically, the given problem is to find a V such that TV equals W. We saw that before. T is the linear map, and you want to find a vector V, find all V maybe, so that TV equals W. It turns out this problem is equivalent to another linear equation. What is that another linear equation? You can take an invertible operator S from W to W. Okay, so T times V has already taken you to W. Now you take an invertible operator S from W to W and then operate on it, compose that to this equation, so to speak. So, okay, so instead of just looking at TV equals W, I look at STV equals SW, and these two are in fact equivalent because S is invertible, right? So it's easy to see why they have to be equivalent, right? So when you have an invertible operator, it's like an isomorphism, you know. So it takes you from invertible operator takes you from input to some other output, but you can also undo that linear operation, right? So it's an invertible operator. You can also go from output to input. So whether you solve TV equals W or STV equals SW, you will get the exact same V's for the exact same W. Nothing will change as long as S is invertible and you've done STV equals SW, then you're the same. Okay. So then S times T, you can design your invertible operator S so that S times T looks like what you want. Okay. So that's the core essential idea behind these elementary row operations and Gaussian elimination. I know if my linear operator, the matrix of the linear operator looks in a specific way, lots of zeros, then I can quickly solve it. Okay. This notion of using operators on the left, okay, S times TV equals S times W, to make ST look like a easier matrix for you to deal with is at the heart of this elementary row operation. So, but be careful about the condition here, right? S needs to be from W to W and it needs to be an invertible operator. You cannot do whatever you want. I mean, if you do some non-invertible operation, then you've lost the solution. Okay, something important to be careful about. Okay. All right. So that's the essential idea behind row operations. Finding the invertible operator S so that ST is of a form suitable for easy solving. So how do you go about finding this operator S? You don't find it in one go. You do it in multiple steps slowly. Okay. So I'll show you how this is done. So once again, I will illustrate it with an example. One example is good enough. Many of you might be already familiar with this, but let's go through this one example and look at it from this operator point of view. Sort of emphasize this, all this knowledge we have about operators and linear maps and what is it that we're doing, as opposed to just the mechanics of how to do it. Okay. So here's a 3 by 3 example. You have Ax equals B being your linear equation, and this A is the matrix shown right there, 0, 2, 3, 3 minus 1, 4, 2, 5, 1, and then you have to solve for the x. Okay. So the first operation I will do, which is an invertible operation, is to permute row 1 with row j to to get a non-zero pivot at 1, 1. So the first step will focus on 1, 1. The 1, 1 entry of the matrix, if you remember from our examples, you want that to be non-zero, right? So can you make 1, 1 non-zero? Okay. So here in this example, 1, 1 has been chosen as 0 for you to illustrate what to do, but below 1, 1 there are non-zero values. So what I will do in the first invertible operation is to interchange row 1 and row 2. Now this is an invertible operation. You can see why this is invertible, right? So you did row 1 and row 2, you can always flip it back, go back to the same old matrix like before when you do multiply by the inverse of this, which is flipping the rows 1 and 2 back again. Okay. So you can do that, but how do you execute that with a matrix? Okay. So for that we can design a nice little invertible operator matrix which represents permuting row 1 and row 2 of anything that's multiplied on the right. Okay. So that matrix I will denote as E1. Okay, just an E1. You can see what I've done here, 0, 1, 0, 1, 0, 0 and 0, 0, 1. Now if you take this A1 and multiply with any matrix on the right, what will happen? Row 1 and row 2 are interchanged. Okay. And you can see clearly that this E1 is also an invertible matrix, right? So it's clearly invertible, it's got full range, no null space. There is it's clearly invertible, and also intuitively you can see interchanging row 1 and 2, you do it once again, you go back to the original state, right? So it's invertible. Okay. So this E1 is a nice little invertible operator, elementary row operator, which gives me this interchange of rows 1 and 2. Okay. And what will I do now? I will take this E1 and multiply both sides of this equation, Ax equals b, sort of transform this equation into another form. So if I do that, I have, instead of Ax equals b, I have E1 Ax equals E1 b, but since E1 is invertible, I know it's exactly equivalent to Ax equals b. If I solve this new equation, I can do the old equation also. Okay. So what happens when after I multiply, the first and second row get interchanged. Okay. So my matrix becomes 3 minus 1, 4. Notice the same interchange happens on the right hand side also. See, E1 multiplies B also. So B2 and B1 also get interchanged. Okay, so this is what happens. This is the first step. There's lots of steps. Like I said, in every step we will use an invertible operator and we'll keep multiplying. And we can do it multiple times, right? So it's not enough. See, I did one invertible operator. I can find one more invertible operator and do the multiplication. As long as it's invertible, as long as I keep multiplying on the left, I know I can undo it and keep go back to the original equation. So that's the principle. Okay, so you do the first operator, that's good enough. It's looking okay now. Already you see the non-zero value is the 1, 1 place, and then there is a 0 below it, right? But you want zeros all the way below, right? If you remember the upper triangular sort of form, I want a non-zero value and then everything should be 0 below that. How do we do that? We can once again use an invertible operator for that. Okay. So right now I am in this form. The next step is to make the pivot value equal to 1. Okay, so the pivot value at 1, 1 is 3 right now. Maybe I don't like 3, I want to make it 1. So what do I do for that? I can divide row 1 by 3. Okay, once again that's an invertible operation. Right, you divided row 1 by 3. How do I go back to the original one? You multiply row 1 by 3 again. Right? So you go back to the original one. So for that there is an operator, and that is a diagonal operator. Okay, so this is a diagonal. The previous one was a permutation sort of operator. This one is a diagonal operator. You see that it has non-zero values only on the diagonal 1 by 3, 1, 1. Okay, and you can see that when this E2 multiplies a matrix, row 1 alone ends up getting divided by 3. The other two rows are not affected. It's retained exactly as it is. Okay, so I will take this E2 and operate with it on my equation. Okay, so I'll do E2 E1 AX equals E2 E1 B, and you see the first row got divided by 3. Okay, so you got 1 minus 1 by 3, 4 by 3, and then other rows remained untouched, exactly the same. Okay, and notice what has happened. This E2 works on the right hand side also. So the B2 became B2 by 3. Okay, so you can see how the equation is getting altered, but retaining the invertibility thing so that you don't lose out on the actual solution. When you find the final solution, it's exactly what you want from the original matrix. Okay, so this is step 1B as I've called it. You can do more now. Okay, so I have 1 on the pivot position. I can make all values below the pivot 0. That's the next step. Okay, so you can see I have 1 in the 1, 1 position. I want everything below it 0. Row 2 already has 0 there, so I don't need to do anything. Row 3 has 2 there. So what will I do? I will write row 3 as row 3 minus 2 times row 1. Okay, once again an invertible operation. I can always undo this I can add 2 times row 1 again to go back to row 3 if I want. So it's invertible, and it's also represented by a nice little matrix that I'm calling as E3 here. Okay, first row remains as it is, second row remains as it is, 1 0 0 0 1 0. What do I do for the third row? I need to do minus 2 times the first row and nothing in the second row, and then 1 in the third row. Okay, so this E3 times a matrix is exactly the operation that I want to do on the row. This is also an elementary row operation. Okay, once I hit my equation with E3, I have this picture where I'm slowly getting the form that I want, right? So there's 1 on the top and then 0 0 below. Okay, so next I want to continue on my upper triangular thing. So I will change my pivot. Instead of pivoting at 1 comma 1, I will go to pivot at 2 comma 2. So that's the next step. But notice once again that this E3 matrix also was operated on the right hand side. Okay, so my B3 became B3 minus 2 B2 by B3. Okay, so it will just become a little bit more messy on the right hand side. It will become simpler on the left hand side, but it doesn't matter. This right hand side is just some value for me. Okay, so now we'll proceed. I've gone to the pivot 2 2 from the pivot 1 1, and I already see that the pivot is non-zero, right? So I don't need to do any permutation to make that pivot non-zero, but it is 2. I have to make it 1, so I'll divide by 2. Divide row 2 by 2. I know already now how to get an operator for that. It's a diagonal operator, 1 half 1, and when I multiply E4 by any matrix on the right, the second row gets divided by 2, right? So that's a nice thing to know. Once I do E4, my operators are increasing in number, so I've just put the dot 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 to indicate it's everything from E4 to E1. You multiply that, I get this nice looking thing, and remember same operator works on the right. Okay, so you get B1 by 2. So you're beginning to get this. Now you can get the picture. Everything below the pivot has to become 0. Okay, that's my next step. And then how do I do that? It's row 3 equals row 3 minus 17 by 3 into row 2. How do I do that? I have an operator for that. I know it's diagonal except for this which row gets involved in the subtraction. You put a minus 17 by 3 and then you multiply with E5, and you see that you get this sort of a matrix. It's becoming messier, but still on the left hand side you see the matrix is becoming really clean, right? So 1 0 0 minus 1 by 3 1 0 in the second column. And what happens in the third column? I have this minus 61 by 6. I know how to take care of that. I will make the pivot at 3 comma 3 1 by multiplying by minus 6 by 61, and I know the operator for that. I know the final form, and look at the final form that we got, right? It is exactly like before, 1 0 0 minus 1 by 3 1 0 4 by 3 3 by 2 1, and we accomplished it by doing a series of invertible operations. Composing invertible operators one after the other, everything is invertible, right? So you can go back easily from one to the other. So we have not lost anything, and from the original equation we have come to this really simplified form. Okay, so here is a summary for you to quickly see what we did, right? We did 6 steps in this, and every step corresponded to an invertible operator, and we saw that Ax equals b, which looked like a form which was difficult for us to handle, but through elementary row operations we got it down to a form which is very, very easy for us to handle. We have done examples exactly like this before, and you know what type of a map that is. It's an invertible map. So every possible b, I will have a unique solution for x1, x2, x3. I know that much just directly from this. Okay, so that's in a nutshell is what elementary row operations are. Okay, so you might ask, what is it in general? Okay, I took a 3 by 3 case. What if the matrix is 100 by 500? What do I do? Okay, what can happen? Turns out you can do something very similar, right? So it's not very difficult to imagine what it is. You just go, start with 1 comma 1 as the pivot, then bring a non-zero value into the pivot, make it 1, make everything below 0, and then you go to 2 comma 2 like that. So now what happens if at some point you cannot find anything non-zero? Then you have to just skip that column and keep proceeding. Okay, so that's the idea. So you go to a particular pivot position, look for a non-zero value there or below. Okay, you don't look above, you look there or below. Okay, well, I want upper triangular, no, I don't care too much about other things. And if you cannot find a non-zero pivot, you simply skip that column, go to the next position in the same row. Okay, so you don't 1 comma 1, 2 comma 2. Suppose in 2 comma 2 you cannot find a pivot, you go to 2 comma 3. Okay, you go to the next column in the same thing. So that I have sort of codified into a little algorithm here, which is what I am calling as the elementary row operations that you can do in general as far as this course is concerned. There are some minor variations here. If you see other linear algebra books and courses, they would do more than just row operations. Some they would do column operations and all that, and then get a much simpler form. But I am sort of resisting from doing column operations. Maybe we will do it later on. For now, row operations are good enough for us. We will live with it. Okay. So here is the little procedure that you can walk through, and you can do this. You can see how I have worked here. I have this counter to maintain which my pivot position, I comma j is my pivot position always. Initially I start with 1 comma 1, and then you shouldn't exceed the boundaries m and n. If you have a non-zero pivot already, you know what to do, right? You divide that row I by that value to make the pivot 1, and then everything below that I am going to make 0 by row operations. Okay? And then once you have made everything 0, I can go to the next row, next column. Okay? I can go pivot to the next row, next column, such way both of them get added. Now in case aij is not equal to 0, you found ij is your pivot position and aij is 0, then there are two possibilities again. Something below I on that same column could be non-zero. Okay? If there exists k greater than I such that akj not equal to 0, then you interchange row I and k. So you have made a non-zero pivot, okay? And then you continue back again. You don't increment I or j. You are the same pivot, but now you have a non-zero pivot. You will come to step 3, non-zero pivot, you will proceed. Okay? But supposing you cannot find anything non-zero below it, okay? Ij is also 0, everything below it is also 0. You simply go to the next column. Okay? You don't increment the row, you go to the next column. Okay? So that's the simple procedure. You can write down a code for it if you like, and you can implement elementary row operations very easily. Today there are a lot of numerical tools out there which will do all this for you. You don't have to do it yourself, but it's good to know elementary row operations. Okay. So what is the major result if you think in terms of structure? Okay. Supposing you do elementary row operations, after that what is the general structure that you will have? Okay. So that's an important question to answer, right? So for any matrix A, there are elementary row operations ei such that if you do them in a proper sequence like I described in the previous algorithm, multiply by A, then you will get a matrix which looks like this. Okay. You could have a few 0 columns. Okay. So I have put a bunch of zeros here. It may happen that you don't have it at all. Okay. So this may not be there, may be empty. Okay, keep that in mind. All these 0 columns that I put may be empty. Okay, so they may not be empty also, but in general they could be not. There could be lot of all 0 columns in the beginning, right? So then you won't find a pivot. You will keep skipping columns. Still you find a non-zero column, right? So that's just sort of like to cover all cases. But usually you will not have these kind of things. So this could be empty also. You may not have all the zeros. So keep that in mind. Then you will find a non-zero pivot. Okay. And then you make everything below the pivot 0, and then you move to 2 comma 2, and there again you may have a bunch of 0 columns, but this also may be empty, right? This also may be empty, keep that in mind. So this may be empty, I am just showing you the general case. This also may be empty. Okay, keep that in mind, and then you will have a non-zero pivot. Okay, so you will keep on going, and then that is how it will proceed. Okay, so any matrix after you have done your row operations will look only like this, a whole bunch of zeros in the lower triangular part, and it will let you infer many things about the range and null directly just by looking at the structure. Linear independence can be quickly figured out, the dimension of the range can be quickly figured out, dimension of the null can be quickly figured out in this form. Okay, so that's the crucial idea. Okay, so that's what I've put here. The rank of A, which if you remember, rank is the dimension of the range of the transform, dimension of the column space. Rank of A is simply equal to the number of non-zero pivots you found. Okay, you can see why that is true, right? So that all you have 1, that will be equal to the rank, that will be the dimension of the range space, right? So that's easy to see. So dimension of null of A is nothing but n minus rank of A. Okay, so once you find out the non-zero pivots, number of non-zero pivots, control everything. Okay, and how do you find a basis for the null of A? Okay, so we found the dimension of the null of A. Supposing you want to find basis for the null of A, all you have to do is to solve for Ax equals 0 using A in this form. After you do this transformation, you can solve for Ax equals 0. Solving for Ax equals 0, also has a very simple procedure, and I will describe that in the next few slides. Okay. But even before that, I want to emphasize that when you are looking at solving linear equations Ax equals b, you can do elementary row operations and reduce any general matrix to a matrix of this form. This is sort of a row reduced form. People do more reductions, by the way. They also do some column operations to have a much simpler form than this, but I'm going to stick to this form. This is enough for us at this point. If we need more reductions, we'll do later. Okay. So this is reduction, and the next step is to figure out more than just the rank and dimension of the null space, how to figure out the basis for the null space. How do you do that? How do you solve the Ax equals 0? I will illustrate that quickly in the next few slides. So now that we've done the elementary row operations, we're now going to see how to use the result of elementary row operations and actually infer something about the range and dimension. We already know how to do dimension of range of A and dimension of null of A quite easily. How do you do further? How do you go further than that? How do you find a basis for the null space is what we're going to see next. Okay. So the first thing is finding the rank of A is very easy. Once you have a form like this, suppose somebody gives you a 4 by 7 matrix A, which you have done elementary row operations for and reduced it to the form that is shown up here on top. You can count the number of non-zero pivots. You can see that you got 3 non-zero pivots. They're not very easy to identify, not very difficult to identify. You got your first non-zero pivot in the 1, 1 place, and then you went to 2, 2 and you couldn't find a non-zero pivot, and then you went to 2, 3, you could find a non-zero pivot, and you went to 3, 3, 3, 4, I'm sorry, and you could find a non-zero pivot, and then after that no non-zero pivots. So you could find 3 non-zero pivots, so the column space is rank 3. You can see the column space is rank 3, right? I mean, those are the places. That's the 3 independent vectors in the columns, and then from there you can infer the dimension of the null. That would end up being 4. Okay. So that's the first step, and the next step to find the basis for the null is to solve this equation, right? Ax equals 0, and Ax equals 0, you know, after these elementary operations you can equivalently solve this matrix, this reduced form matrix, times x equal to 0. Okay. How do you go about solving this? For even for this there is a very simple process. You can maybe quickly infer something here, but let me give you a systematic way to go through this. So what you do is, you first identify the variables corresponding to the non-zero pivot positions. What are the non-zero pivot columns? In the first column, third column and the fourth column you found non-zero pivots. So your first variable, which actually multiplies the first column, and the third variable which multiplies the third column, and the fourth variable which multiplies the fourth column become your dependent variables. All the other variables x2, x5, x6, x7 become free variables. And you see clearly the number of free variables is equal to the dimension of the null space. All these are not coincidences. They are, they've come because of the very reason why null space and dimension all are defined. Okay, so you identify your dependent variables and you identify your free variables, and then you can solve for the basis of the null space or the set of all solutions for Ax equals 0. How do you go about doing that? Here is how you do it. Okay. So once again I have this reduced form for the matrix. I have identified my free variables. I know what my free variables are. I have to assume some values for the free variables. What values do I assume? You assume values like the standard basis. You have free variables, 4 of them in number. So you assume in the first case that the free variables will take values 0, 0, 0, 1. And 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. I mean, technically you can assume these to be any 4 linearly independent length 4 vectors. I am simply taking them to be standard bases. That's very common. Okay, so you take them like this. Okay, once you assume values for the free variables, it turns out the dependent variables can be solved for. So you solve for the dependent variables so that Ax equals 0. Okay, so the equation is Ax equals 0. The free variables are known to you, 4 free variables are given to you. You can solve for the dependent variables and your solution will be unique. Okay, you can also imagine and think why that should be true. Once you put values for the free variables, right, you end up having the remaining variables give you like an injective map, right? So you will have a unique solution, and that unique solution you have to find by solving. So let me show you maybe one example alone, and then I will leave you to do the other ones. Okay. Let me take the first example where I put x2, x5, x6, x7 as 0, 0, 0, 1. Remember, it's sometimes I will find it convenient to write the variables on top of the columns, just to quickly identify, otherwise we will keep going back and forth. Even if you write it as a vector on the right, it's easy to identify the variables like this. So I like to write it like this, and then if you put x2, x5, x6, x7 as 0, 0, 0, 1, and you're solving for ax equals 0, right? So you're solving for ax equals 0, remember that, that's very important to remember. Okay. When you're solving for that, it's just easy to see, right? So you put x2 0, x5, x6, x7 0, and you want to solve for the dependent variables. You start with the lowest variable, so to speak, the lowest equation you start with, okay, because it's upper triangular. You start with the lowest equation and then you go back. What is your lowest equation? Like x4, no? If you see x4 plus 7x5 plus 6x plus 8x6 plus 4x7 equals 0, that's your equation. Now x5 and x6 are 0, x7 alone is 1, so you basically have x4 plus 4 equal to 0, which gives you x4 equals minus 4. Okay, so you've got x4 here. Then you go to the next equation above it. Once you solved x4, you can go to x3, and that equation is x3. Okay, so x4 you already solved as minus 4, so minus 12, and then x5 and x6 are 0, then x7 is 1 plus 2 equals 0, and that gives you x3 equals 10, which is what I've put here. Okay, so x3 is 10, and then you go to the first equation, there you get x1, okay, and then x2 is 0, x3 is 10, so plus 30, okay, and x4 is minus 4, so minus 12, then x5 and x6 are 0, and then x7 is 1 plus 7 equals 0, and that you can check will give you 30 minus 12. Did I get that right? Maybe I made a small mistake here. Let me just check that once again. I think there is a mistake here. So you have x1 plus 30 minus, oh no, this is not 12, this is 16, right? Yeah, you're right. So that's correct. So I didn't make a mistake. So x1 plus 30 minus 16, because it's 4 times 4, minus 4, it's minus 16 plus 7 equals 0, and that will give you x1 equals minus 21. So that's what I got here. Okay. So x1, x3, x4 is minus 21, 10, minus 4, x2, x5, x6, x7 is 0, 0, 0, 1. You put them all together, you get your v1. So this is one basis vector for the null space. Okay. The reason why it becomes a basis vector and all will be clear to you, but this is one vector which definitely belongs to the null space. There is no doubt about it, right? If you find 4 linearly independent vectors in the null space, you're done. You know the dimension is 4. So I have found one vector in the null space. Okay, why it's linearly independent, you'll sort of quickly see because of this 0, 0, 0, 1, it will become linearly independent. Okay, so likewise you proceed. For the next set of values 0, 0, 1, 0, you proceed in the same way. I'm not going to show you the details for this. You can see how to proceed. Just put the values exactly like the same way I described before. Start from the bottom, keep solving, you will get this other vector v2. So v1 belongs to null space, v2 belongs to null space. Likewise v3, again put 0, 1, 0, 0, solve for the free variables, solve for the dependent variables, you know v3, right? And then you put 1, 0, 0, 0, this is the easiest to solve, everything else becomes 0, only the first equation matters. So you can put minus 2, 1, 0, 0. So you get v4. So now it's important to quickly realize that the basis for the null space will become v1, v2, v3, v4. Why? Because v1, v2, v3, v4 clearly belong to the null space. A v1 equals 0, a v2 equals 0. We have solved for it like that. And additionally, they are linearly independent. Why? Just look at the free positions. You will get like an identity matrix there, right? So 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. So they cannot have any linear dependency between them. You have found 4 vectors which are linearly independent in the null space, and that gives you a basis. Okay, so very simple process. I'm sure you must have seen some version of this process before, but this is the logic for why it works. Okay, so that's how you solve for the null space. Okay, so you see that the elementary row operations tell you the dimension of the range, dimension of the null. They also allow you to solve for a basis for the null space. Of course, when it's a little bit of computation, but you can do it quite easily. Okay, so now how do you solve for Ax equals b? Okay, I solved for the null space. We also saw that once you know the null space, once you know whether it's in the range or not, it's easy to figure out the solution. So let me just walk you through how you solve for Ax equals b. Okay, so the way you do it is the following. Okay, so you simply set the free variables to be 0, 0, 0, 0. Okay, you can set it to be anything else also, it does not matter what you set it to be. I will set it as 0 0 0 0 because it gets rid of all my columns in the matrix, it becomes much simpler. So, you simply set it as 0 0 0 0 and solve for dependent variables so that Ax equals b. Okay. So, in that equation things will be much clearer. It is very simple. First of all, it will be an upper triangular matrix, and with some 0 you can quickly identify whether or not solutions are going to exist or not. It is very easy to see that. So, it just gets rid of all your dependent variable and free variables. You only have your dependent variable. So, maybe I should write the simpler equation. So, once you put 0 0 0 0, you just have this equation, right. So, you have 1 0 0 0, 3 1 0 0, 4 3 1 0, and that is it. That times my dependent variables are x1, x3, x4, and that needs to be equal to 1 2 3 0. Okay, it will be in this form, it will be in your reduced form, right, and it will have all the ones coming one after the other. There will be none of these nasty zeros in the middle which confuse you. Okay, so it will be just all ones together, and you can quickly solve for this. Okay, first of all, you can identify that any 0 row here also corresponds to a 0 on the right hand side. If there is an all 0 row here and it does not correspond to a 0 on the right hand side, what can you conclude? You can conclude that there is no solution. But in this case, the 0 here corresponds to a 0 there. So, I know that there is a solution, and then I can quickly read out what will be the solution for x1, x3, x4. I start with solving for x4 first. X4 ends up being 3, and then use that in the previous equation and get x3, use those two in the previous equation, get x1. Very simple process. One can follow that and then solve for it. Okay. So, that is what I have done here, and such a solution is called a particular solution. It is one vector in the solution. Okay. So, it is one value of v such that Tv equals w. Okay. One solution for x. But now look at this particular case. This particular matrix corresponds to a linear map which is not surjective, it is not injective also, right. So, then what do I expect? I expect if the value of b is in the range, I expect infinitely many solutions. Value of b was in the range, I saw before that the 0 rows corresponded to 0 values on the right hand side. So, all I have to check is find the null space and I will have a full solution. Okay. So, the entire solution is u plus null a. The solution will have a picture like this. This u particular solution plus any linear combination of the null space basis vectors. So, this is the set of all solutions for this. Okay. Hopefully, this gave you a very clear view of how things will look and how you can find solutions for linear equation. Now, I also told you the other case where you could have no solution. Okay, right? This is a linear map which is not surjective, not injective. So, if you have a vector outside of the range, then you may not have. So, how do you identify? And you see that will also happen very easily, right? So, here when I try to solve for the particular equation, what will happen? I will put my free variables as 0 0 0 0. Then I will get an equation where you will have an inconsistency. There will be an all 0 row on the left hand side, it will correspond to a non-zero value on the right hand side, right. So, look at this value and look at all these guys. Okay. So, there will be no solution corresponding to this. Okay. So, this will always happen because in this row reduced form, you see this will be the only way in which you can have no solution, right. So, otherwise you will have a fully invertible sort of upper triangular form. Okay. So, from there you can conclude there is no solution. Okay. So, hopefully this tells you what to do for given any linear equation Ax equals b. You do a series of elementary row operations, reduce it to the form, the row reduced form, identify free variables, identify dependent variables, find your dimension for null, find the basis for the null space, and then when you want to solve for Ax equals b, find a particular solution, and there you may have a solution, you may not have a solution. If you have a solution, then the entire solution set is that solution plus the null space. If the null space is trivial, then you have unique solution, otherwise you have infinitely many solutions, and if your b is not even in the range, then you do not have a solution at all. Okay. So, that is in simple terms how to solve linear equation using these elementary row operations in general. Okay. So, I have set up a small quiz for you. You can go through and answer the questions in this quiz. It will give me very good feedback and will also give you a good brush up of all that you have learnt here, and be sure that you can you can be sure of some of the concepts and get it reinforced. Okay, thank you very much.